Electric field due to a uniformly charged ring. Objective: to derive the electric field on the axis of a uniformly charged ring. Consider a uniform charge distribution in the shape of a ring. Let the radius of the ring be A and charge contained in it be Q. Let P be a point on its axis at a distance x from the center. Consider an infinitely small arc with charge dq on the ring. We can consider this small arc as point A. Let AP make an angle alpha with the axis of the ring. The distance of this element from P, r, is square root of a square plus x square. The electric field at point P due to dq is along AP, and its magnitude is kdq by r square. The component of dE along the axis is dE cos alpha, and that perpendicular to the axis is dE sin alpha. All such elements on the ring make the same angle alpha at point P. When all such differential elements are considered, we can see from the symmetry that the components perpendicular to the axis cancel out each other, and components along the axis add up. The magnitude of electric field due to the ring along the axis will be integral of dE cos alpha. Substituting dE in it, values of k, alpha and r are constant for all the elements on the ring. Hence, they can be taken out of the integral. On integrating over the whole charge of the ring, we get E is equal to kq by r square cos alpha. Cos alpha is equal to x by r. So E is equal to kqx by r cube. Substituting r with root over a square plus x square, magnitude of electric field due to the ring along the axis becomes kq by a square plus x square, the whole to the power 3 by 2 into x. Summary: magnitude of the electric field due to a ring along the axis is kq by r square cos alpha, or kq by a square plus x square, the whole to the power 3 by 2 into x.